Hello, my name is Dan Sotolongo, and I'm here with Daniel Knowles and Fabian Hueske to talk about watermarks in stream processing systems. So we're going to start with concepts and a little bit of context and motivation for watermarks. Now, we're working in the context of stream processing. So we have a system that needs to do potentially complex data transformations, and it needs to do them as fast as it can. Now, a problem arises because our transport might reorder or delay data, which makes it challenging to reason about when the system has enough data to make good decisions. Now, we call this the problem of completeness. It's hard to tell the difference between not seeing a record because it doesn't exist and not seeing a record because it hasn't arrived yet. So whenever we want to do some processing that depends on the absence of data, things get complicated. To make the problem more concrete, consider the example. Say we have a customer service system and we want to figure out which customers have been kept waiting longer than a minute. Logically, you can express that idea as the SQL query on the right. Watermarks are a solution to the problem of completeness. This figure shows one way to think about watermarks. When events happen out in the real world, they're totally ordered by the times that they occur. This is represented by the top timeline, where events are change color as time goes by. However, recording and transporting those events introduces variable delays to them. The bottom timeline shows what a stream processing system might observe in practice, with delays and reordering. One way to think about watermarks is as a clock on the event time of an out-of-order event stream. Looking at the diagram, you can see two clocks, one on each timeline. These clocks represent the same time. All of the events from purple to orange happened before that. The top clock is a physical clock. When you read it, it means that everything to the left of it already happened. The bottom clock is a watermark, which means that the same thing, but maybe with some events from the future sneaking in. So if we go back to the example of finding long waiting customers, when we see a watermark with some time t, it means that all calls before t minus 1 minute without responses have been kept waiting for a minute. That's the general idea of a watermark. But we can connect that to how they work in stream processing systems. We think of such systems as Dataflow graphs with vertices representing stateful operators and messages being delivered between the vertices along edges. There are three roles nodes can play in the graph. First, sources read data from outside of the system and introduce it to the Dataflow system. They have to generate a watermark for the stream of data that they're producing. If the system they're reading from supports watermarks, that job is easy. But most systems, like PubSubs or Kafkas or file systems, don't provide that mechanism. So in practice, most users rely on various heuristics to estimate watermarks. Now, the heuristics can be wrong, which leads to the problem of late data, events that show up after the watermark claimed they wouldn't. But both of these topics are deep and complex, so I encourage questions in reading the paper for more details. The second role is operators that have both incoming and outgoing edges. Such nodes have to propagate their input watermarks onto their output edges. There are two common patterns that emerge for this kind of propagation. Many stateless operators, like projections and filters, don't change timestamps of the records they're processing. So they simply take the minimum of the watermarks on their incoming edges and produce that on their outgoing edges. On the other hand, stateful operators like group by or distinct often aggregate multiple events into a single output. The timestamp of such an output is usually a function of the timestamps of the inputs, like it might be the max. So the operator delays the output watermark according to the events it has buffered in its state. Finally, operators consume watermarks when they depend on completeness to determine whether they can produce outputs. The most general mechanism for consuming watermarks is watermark timers. The operator registers a callback to be invoked when the watermark exceeds a certain time. For example, in our customer service example, an operator might set a timer for each call event 1 minute after the time of the call. If the timer fires and no corresponding response has been received, the customer has been waiting longer than a minute. Now, these three roles can be combined in sophisticated stream processing systems, as has been shown by users of Dataflow and Flink. There are numerous alternative approaches to watermarks. One popular example is the idea of bounded disorder, where the distribution of event delays is assumed to have some fixed range. Now, we argue that watermarks offer benefits over these other approaches for several reasons. First, they're dynamic. If delays increase, watermarks can adapt and not drop large amounts of data. Conversely, if delays decrease, watermarks can catch up, allowing systems to produce outputs more quickly. Secondly, they're non-blocking. Operators opt in to waiting for completeness, while operators that don't need it don't have to wait. Third, they're customizable. Different implementations can trade between simplicity and accuracy according to the use case without affecting the logic of the processing system. So watermarks abstract over many possible notions of completeness. These benefits make them a powerful tool for implementers of stream processing systems. So now I'm going to hand it off to Fabian to talk about the implementations.
Yes, in the paper, we discussed the implementation of two popular stream processing systems, namely Cloud Dataflow and Apache Flink. Those two systems have very different implementations for the watermark system. In Cloud Dataflow, uses a central aggregator aggregation service to aggregate watermarks and broadcast them to downstream operators. And this, in a nutshell, this works as follows. Each worker node maintains an in-memory histogram of buffered timestamps and computes the minimum observed timestamp from that and reports this to the aggregator node. The aggregator node collects all the reported watermarks of the parallel nodes for a certain operator, periodically aggregates these reports and sends them out to all tasks, to all downstream tasks that receive input from the operator for which the watermark was aggregated. And then each node computes its own watermark as the minimum of its local watermark and the watermarks that it got from the reporting aggregation service. In Apache Flink, this works a little bit different. Flink uses an approach that inlines the watermarks in the data channels to distribute them to the downstream nodes. A source node monitors here the events that get injected into the data flow and produces watermarks. And these watermarks are forwarded by broadcasting them across all data channels. These watermarks are then inlined in the data channels. They don't overpass the records, and the nodes that receive the watermarks have to aggregate them themselves. So here, they basically each operator is doing the aggregation job that for which Cloud Dataflow uses a separate service. Yeah, and in the evaluation, we compare the implementation, these two implementations, and see how they perform. And I hand it over to Daniel for the evaluation section.
Yeah, so for the evaluation here, we wrote up some pipelines using Apache Beam, which is an SDK for writing pipelines that has implementations in both Flink and Dataflow. So what our pipeline did is it just generated a bunch of records with known timestamps so that we know when the watermark would advance. And then after some shuffles in the pipeline, we set timers to and then evaluated how long it took between the watermark advancing and the timers firing. So we evaluated this across a couple of dimensions. The first one was just as we add more workers. And what you see here is that in Flink, adding more workers generally doesn't affect the watermark. And in Dataflow, it actually improves things somewhat. And this is because the shuffles actually get more consistent, lower latency as you add more workers. And the watermark propagation is dependent on the speed of the shuffle. The other dimension we took a look at was throughput, just to see how adding more load into the system affects watermarks. And what we see in both systems is as you add more records, there is a mild upward trend in latency as the overall system just becomes more loaded and slows down a little bit, but it's not significant. What you see in both of these is that we can implement watermarks well on large-scale distributed systems with fairly low latency. There's a couple trade-offs between the implementations. So first, the overall latency is higher in Dataflow due to relying on the central aggregator and like periodic reports to it. On the other side, though, for fault recovery, Dataflow tends to recover much more quickly because everything is based on this distributed state, which is continuously checkpointed, whereas Flink does periodic checkpoints across the entire system. And finally, idle workers in Flink pipelines require a little bit of special handling because if there's no records flowing through a node, there's also no watermarks being propagated, which then delays the watermarks across the entire pipeline. So Flink needs to do extra work to keep those up to date. Yeah, in conclusion, so watermarks are essentially a clock for event time, and they provide a couple of key benefits, namely dynamic disorder handling, non-blocking consumption, and a high degree of customizability. And what we've shown is that multiple implementations work with some different trade-offs, both using a central aggregator or doing inline propagation of watermarks in the data channel. And that's all. Thank you.